Welcome all. How are you guys today? I'm glad to hear it. I hope you guys are well. I hope this doesn't look change that. It is Monday or happiest day of the week. All right, so this time it is recording. So I want to talk about image formation by optical devices. We've been over this a little bit in lab already. So I'll go through this a little quicker than I normally would. But if any of it doesn't land, please make sure that it's explained to your satisfaction. Sadly, this is one of those times where it would help if you had a better art teacher or a better artist for a teacher. But if we had an object, and for simplicity's sake, I'm just going to pick one point on the object, but note that this could be right. I'm only going to pick one point. As our object. But it could be any point on the object. In fact, every point on the object I want you to think is doing just this. We could say that every point is giving an infinite number of rays. One, this class isn't infinitely long, even if you think it is. So I'm not going to do that. But two would clutter the board too much to try. So I'm just going to draw a few rays. And so if this is a mirror, how does this ray reflect?
Would be reflect back.
How so? Help me describe the direction.
Firstly, you draw normal perpendicular with the surface, and then you reflect exactly the symmetry respect with that normal style.
I like that. Sadly, I'm incapable of actually drawing that, but it's the thought that counts. So since this is a mirror, I'm putting the observer on this side of the mirror, right? It wouldn't make sense to put the observer back here because those rays wouldn't reach him or her, yeah? I could also, I don't know, draw a ray like this. How's this one going to reflect?
Directly back.
Straight back from whence it came, right? I could go with that. How does that one reflect?
Reflect with respect to a normal and still a mirror image.
Like that?
Yes.
Yay? I'd add more in, but I'm running out of colors and I'm lazy. So these rays, according to the observer, all seem to diverge from this point. And so that's where the observer says that the image is. This image is virtual, right? because where the observer sees the rays diverge from, there aren't actually rays diverging from that point. Yeah? So virtual. This is kind of just applying our law of reflection, right, to a flat mirror. So we would have said it was a real image if there actually had been rays diverging from the point where we see, where we say that the rays diverge from. Yeah? We talked about this also in lab, but lateral magnification. Use capital M for this. And it's just the image height divided by the object height. Because I'm too lazy to write that out most of the time, I'm use h prime over h. Hooray? Hooray for my laziness? It's the happiest day of the week. Come on. Note that this point is at the same height along the mirror, this image is at the same height along the mirror as the object was, yeah? And so here for our flat mirror, our plane mirror, I could draw the rest of the dog, right? I would go here. Right. So there's some preservation of this here. I want to define my object distance and my image distance here. And so I'm going to pick P and I'm going to pick Q. This we could also say is S object and S image.
They're the same.
Yeah. Because I'm lazy, it's easier for me to write P than SO, and it's easier for me to write Q than SI. That way, you guys don't have to ask, is that an O or an I?
I like P and Q more than S and S.
P and Q gets used a lot in physics and engineering. There's an expression, mind your P's and Q's. And I don't know chicken and the egg, which one came first, but.
Statistics use S for the simple standard deviation.
We use that in physics too, so. So more often than not, you're gonna, in these problems, see me use P's and Q's. Just as a heads up. So in this case, for our flat mirror, the image is equally far behind the mirror as the object is in front of the mirror. That's all right? So this gives us an unmagnified virtual and upright. So virtual image. Yay? Does have front to back reversal. So front would be, I don't know, on the right here, and it's on the left here. Yay? So let's talk about spherical segment mirrors then. So I'm going to start with our concave mirror. Not that I can draw either of these. Not terrible. You guys are a tough audience. That would be the center of curvature. Yay. Mm-hmm. So let's do what we did here, where I don't know what colors I used, I don't care. Where if that is our ray, how does this thing reflect?
You have to make a tangent line and then to see.
Does that seem reasonable-ish?
Yes, kind of.
As my normal?
Normal. Oh, okay, yeah, you can do that. Yeah.
Wait, it wouldn't be straight back?
Does that seem
Yeah, that
reasonable?
seems reasonable.
Better. So then what happens?
Does it not go straight back?
Goes straight back. Why?
Because there's no angle between the normal and the incident rays.
Because something that passes through our center and strikes the surface of a spherical bodied mirror, that is a radial line, right? Mm-hmm. And the radius is perpendicular to the mirror surface. Yeah? Mm-hmm. So we're sort of happy with that?
So in this scenario, each ray will go back where it points from.
Yep. That's okay?
Yeah.
So then, let me keep our normal, but get rid of that ray to the best of my ability. So now let's put so if this is the center, right? Let's put our object here. Now, oh good golly, how am I going to do this? Clearly not well.
Small angle.
So how does this reflect?
Go down. No, go down.
So something in that family, is that true?
Yeah.
Is that all right? And
You need another normal then.
I do. And so the normal for this, right? So we pretend that we started at the center. Is that as terrible as I think it is?
So all
Like,
normals
kind
need
of.
to go through the center point C, right?
So if I trace the normals back, it should come through C.
Oh, okay.
Yay? And so here. Yeah, it's really something. That's not actually as terrible as I feared. So you can see it's a little off axis, right? It's a little too high. But this is my effort at kind of a focus point. In truth, because of something called spherical aberration, it's really only paraxial rays that exactly go through the focal point. And so, but in our idealized case where this angle is small, then every ray is practically paraxial. And so, let's say then that oh goodness. Yay. That I'm going to define my focal point as the point that, for the concave mirror at least, that paraxial rays are reflected through. And that's okay? All right. So if I try to badly draw this for you, which is my specialty, this has a fairly large radius of curvature. It's not my best work, but it's not my worst. If we put our object height h in front of the mirror, then probably, let me curve this more. I went overboard with trying to make this big enough to see without. So now Does that seem reasonable-ish?
Wow. This is the best circle I've ever seen you draw.
Oh, so when I was an undergrad, I took E&M from Mihiko Suzuki, who was one of the first people to propose well, his version was non-symmetrized, but a version of string theory. He could just like freehand perfect circles. He could write with both hands. I mean, it was
It's left hand.
it was intimidating being in his class. He was, I'm sure he still is, but I also had a class from his daughter, who is now a tenured professor at Stanford, but she was at Berkeley for a while. Okay, so close enough, yeah?
Yeah.
So the center of this thing would be here. I'm going to just draw a couple of rays to make my life a little bit simpler. And I feel like I don't have the colors enough to make this work, but we'll try. Wish I had a straight edge. That's not terrible?
Good.
Okay. And then note that, as we just pointed out, if we send it through the center, it should do something like that, yeah? And so, what does this imply about the image that we get? First of all, where is it?
So the bottom should be also in that.
So notice these rays came from a point at the tip of the arrow. And so the image of this should do that. Yeah? And so if this is the object, then this is the image. Yay? Because my drawing leaves a lot to be desired, can I kind of cheat the drawing a little? Let's draw, I used that one, yeah. Something like that. Doesn't seem fair, but oh well. And then I used this guy, right? Does that at least sort of seem fair?
You're just copying what was inside there.
Yeah, I just wanted to grab this and this,
Oh, okay.
and the dashed. That's okay?
Yeah, thanks.
I'm going to call this angle alpha, I'll call this angle alpha, and at least in my notes I called this one theta. Wow, that's not going to show up at all on video. alpha, alpha, theta. Yay? And then this is H, and this is H prime. Yay? So, by our kind of statements here, what should I call this distance?
H.
P plus Q.
How about P? Right, the distance from the mirror to the object?
Oh,
What should I call this distance? Q. What should I call this distance?
Is it F?
R.
R.
Are you really? I was hoping.
Are you mocking my... Sarah, I should get my monies back for, like, I don't know, a decade's worth of Community Art 1, because they're still making fun of me. This one in particular. She can't see you, don't worry. She also, I guarantee, even if I sent her the link, wouldn't watch it. I actually have to pay her to look at my drawings. It's the only way she'll do it. So if we had tan of theta, what's it equal to? This isn't entirely fair, 'cause
Over
H
H
prime
over R.
Q.
How about-
Q? You're using those the right side?
let's use H and then let's use H prime. So let's use, I'm going to write this twice. In terms of H, what do we have?
H over P minus R?
Look at this triangle.
Oh,
H divided by, what's that O2 there?
All right.
E.
Maybe they make fun of me for a reason.
Is it?
H over P.
Yeah.
So that means it's H over
H over P.
Yeah?
what is P? Oh, okay.
Yeah.
So, but there's another way we could write this in terms of H prime.
Would it be H prime over
Q?
Oh, negative
Yay?
H. Why is it negative?
Because note that
Okay.
we're happy-ish. So if we have that we want lateral magnification to be, we want lateral magnification to be H prime over H, can you help me out with that?
Tangent theta Q over tangent theta P. Or I guess just Q over P.
Modulo a minus sign. Yay? Let's use another board so that What if I wanted to look at tangent of alpha? Let's do it first in terms of h.
H over P minus R.
Say this again?
H over P minus R.
We're happy? Okay. What if we wanted to look at tangent alpha in terms of h prime?
Would be negative h prime over r minus q
Over,
over r minus.
correct.
Why isn't negative again?
Because it's under the dash line.
I would consider that 0.
Yes. That's how we're gonna treat this.
We treat it as an axis. Right?
Yeah. So we can put these two together.
How about I want
Oh, wait,
the
I need H prime here.
absolute value there, like I tired like P with R with P. I just put the absolute value like who is number size like P minus R minus whatever. Like I can put the absolute.
I don't think
value.
that would affect your overall answer, although we want the minus sign because ultimately it's going to tell us whether the image winds up being upright or inverted.
Oh, okay.
So, I don't want to call that h prime. What was I doing there? So if we again said that m is h prime over h, what do we get this time? Yay? And I let this be equation 2. And so then, now we have two different tellings of h prime over h. And so what can we do?
Make them equal to each other.
Set them equal, such that so far so good?
Where did the negative sign went away?
Because they both had a minus sign.
Oh,
If you want, I can put them back. It's not.
no, it's fine.
Okay. Then we could cross multiply r minus q times p is equal to q times p minus r. And so we get that r times p minus qp is equal to qp minus r times q. I can gather terms. I gathered them such that I put 2qp is equal to rp plus rq. Yay. And then I divided both sides by the product QP, and I divided both sides by R. Yay? Note that P over QP is 1 over Q. Q over QP is 1 over P. And we get that 2 over R is equal to 1 over Q plus 1 over P. But what did we say the focal length is equal to? Focal length is half the radius. So 2 over R is equal to what?
1 over F.
1 over F. We can say that 1 over F is 1 over P plus 1 over Q. Yay? So for mirrors, for this version of the equation, so some books, I know some of you aren't using Knight. Some books will give you this equation that 1 over F plus 1 over P is equal to 1 over Q. The designations I'm giving you here are not for that equation, they're for this version of the equation. And it just defines where P is meant to be positive. So if you're using 1 over F is 1 over P plus 1 over Q, then P and Q are positive on the real side, and P and Q are obviously negative on the other side. Yay? So our general sign conventions, some of this is repeated because I just wrote it up there, but Sorry, this is the world's longest. Board writing. Okay. With apologies. So sign conventions that we're going to use for mirrors. The object position P will be positive for a real object in front of the mirror or negative for a virtual object behind the mirror. That's going to necessitate a second optical device to where the image of the first device is used as the object for this mirror. So you can put the image behind the mirror, right? Image position Q will be positive for a real image in front of the mirror and negative for a virtual image behind the mirror. The image height, H prime, will be positive for upright images, negative for inverted images. Focal lengths and radii, F and R respectively, positive for concave mirrors, negative for convex mirrors, and the magnification will be positive for upright images and negative for inverted images. Yay? Are you guys okay with ray tracing at this point? I've done it a couple times in lab for spherical segment mirrors. We're okay or we're not okay?
For concave, convex, that's mirrors or lenses?
This is sign conventions for mirrors. I'll give you sign conventions for lenses in a while. I don't know if I'll get all the way there today, but I'll, if not, then early Wednesday. This is okay? Okay, so ray tracing for spherical segment mirrors, do you need to see this or are you happy?
If it's going to in the exam, please show us.
Okay, but I've also done it in lab twice, so I am hoping that it's in your notes somewhere. Oh, it's hideous. So ray comes in praxially, what's it do? Comes
It goes to the lens.
through the focus point. Okay? Well, that seems unnecessary. Comes through the focus point on its way to the mirror. What's this one do? Exits or reflects paraxially. Right, it's kind of the opposite of this. This one came in paraxially, comes through the focus. The other one comes through the focus, comes out paraxially. we're happy-ish. And then the other one I like to recommend strikes the yay. So if this is our object, where is our image?